2011, an ordinary star brightened for no visible reason. Astronomers suspected a black hole had passed in front of it, confirming that suspicion required 11 years of Hubble measurements. Now Rubin is looking for more candidates. This is Cosmion. Point it at any question in the universe, and it will show you the answer, whether you can bear it or not. So let's go back to that star, because the strange part is that the black hole itself never appeared. At first, all astronomers saw was the star growing brighter, reaching a smooth peak, and then fading back to normal. It stayed in the same crowded patch of sky, while the stars around it carried on as usual. That smooth rise and fall had a name: gravitational microlensing. The hidden object added no light of its own, so the extra brightness still came from the distant star. Nothing touched the star either. The two objects only lined up from where we happened to be watching. Microlensing is useful for a black hole traveling alone because it has no bright companion and usually no glowing disk to give it away. Here's the problem though. A brightening star tells you something passed in front, but it doesn't tell you exactly what it was. Picture a distant star, a hidden object, and Earth. For a moment, they almost line up. The hidden object's gravity bends the starlight. That sends more towards Earth, so the star looks brighter. When the alignment breaks, the star fades. That's gravitational microlensing. Now comes the tricky part, because astronomers call the hidden object the lens, and a black hole is only one possible lens. A heavy object may create a long event, but a lighter object moving slowly can stretch the brightening as well. So that brightness graph, called a light curve, gives astronomers a strong clue and a target to study, but it still isn't a verdict. To get closer to an answer, they needed another measurement, so they returned to the star and precisely measured where it appeared. The same gravity that makes the star look brighter also nudges its apparent position by a tiny amount. That nudge is far too small for our eyes, but a telescope like Hubble can measure it against nearby stars. Astronomers call this astrometric microlensing. That first word simply means they're measuring precisely where the star appears in the sky. When they combine that tiny shift with the brightening pattern, they can begin to untangle the lens's mass, distance, and movement. For the 2011 event, Hubble kept returning after the main brightening ended, building a measurement record that eventually covered 11 years. Those measurements pointed to a lens weighing about 7 times as much as our Sun. The team then looked for light from the lens, because an ordinary star with that much mass should reveal itself. The team could not detect any light from the lens. In 2025, the researchers concluded it was an isolated stellar mass black hole. That means it formed when a massive star died and now travels without a companion. Hubble never took a glowing picture of it. Instead, it measured the tiny changes the black hole's gravity had caused in another star's light. That solved one mystery, but it also showed why finding a whole population this way would be painfully slow. This is where Rubin changes the search, because it can look for the first clue across an enormous part of the sky. Rubin began its 10-year legacy survey of space and time in June 2026 from a mountaintop site in Chile. Every few nights, the observatory scans huge areas of the southern sky, returning to the same places again and again. During those 10 years, each patch should be visited about 800 times on average, using different color filters and under different conditions. Put those visits together, and a single point of light becomes a history, showing when it brightened and when it faded. A smooth microlensing pattern can then be flagged for closer study. Scientists at NOIRLab expect Rubin to record more than 10,000 microlensing events during the survey, with black holes responsible for many of them. That doesn't mean 10,000 black holes, because each event begins with a hidden lens whose identity is still unknown. Longer events can move up the follow-up list, but they are still candidates until other observations reveal what the hidden lens actually is. Rubin finds the promising brightening, and sharper follow-up observations can then help constrain the mass of the hidden object. So how do you find an invisible black hole? First, you watch a visible star and record how its brightness changes. Then, you measure its tiny shift in position, because the two records help astronomers narrow down the hidden lens's mass, distance, and motion. If the mass fits a black hole and no starlight is detected from the lens, the case becomes strong. The event first seen in 2011 was confirmed this way in 2025. With Rubin, astronomers can begin with a survey of candidates, then focus precious follow-up time on the ones that look most promising. Finding one black hole is exciting, but a large sample could show how many wander through the Milky Way. Once astronomers know their masses, distances, and movements, they can test how massive stars die and what happens to the black holes left behind. Some newborn black holes may remain near where their parent stars collapsed, while others may be kicked across the galaxy. So black holes born from dead stars may be drifting through those gaps unseen until another star's light gives them away. Subscribe to Cosmion, because next we're following those newborn black holes and asking how one can be kicked across the galaxy